Okay, so next up we have a very exciting speaker from NVIDIA. Please welcome Naman Govil.
Good afternoon, folks. I'm Naman. I'm very excited to be here. So just a quick note before we start, like what I'm sharing with you today are my personal thoughts, right? These don't represent the thoughts or views of NVIDIA or any other prior employer of mine. Right, so the first thing I like to set up is talk to you about what I'm going to talk to you about today, right? So we are all experiencing that like modern deep learning is a very fast evolving field, right? With continuous breakthroughs in model architecture, training techniques, and optimization strategies, right? These advancements are deeply intertwined with hardware innovations, making it crucial to consider deep learning from a hardware perspective, right? As models grow in size and complexity, with the addition of new ultra low latency targets like high energy efficiency demands, leveraging hardware capabilities holds the key to next level optimizations, right? As AI continues to push boundaries, the next major breakthrough will come from a holistic hardware software co-design, right? Ensuring that deep learning models remain scalable, efficient, and accessible. So today, I want to take you on a journey to approach deep learning from the hardware perspective. Right? We learn more about the capabilities and constraints of hardware and how to take advantage of them. Right? What I want you to walk away from this talk with like interest and curiosity for approaching software optimizations with hardware in mind. So let's start at the very beginning, right? So like what is it at the core, right, of all of deep learning that we are executing on the hardware? Right? It's very simple. It's these simple matrix multiply. Right? That is, you take like a tensor or a matrix A of size m rows by k columns, right? You multiply that with another matrix B of size k by n, and then you produce an output of size m by n, right? Pretty simple. And when we think in terms of hardware, right, in terms of measuring or estimating performance on hardware, we all often think in terms of like flops and bytes, right? Flops are essentially floating point operations per second, right? It's the number of arithmetic operations that you're doing per second. So for this simple matrix multiply, you are the ops that you're doing are essentially multiplying m times n times k, right? And then there's also a times 2 because you're also doing an addition per pair that you multiply. Right? And the bytes that you read or write for this operation are the size of the matrices. So you read A of size m by k, plus you read B of size k by n, right? And then you write the result of size m by n, right? That's our base. So with this base setup, right, now let's zoom out, right, and see where do we find all of these like matrix multiply operations, right? Spoiler alert, everywhere. So I've drawn this like high-level diagram, right, of a decoder block of a vanilla transformer-based model, right, that takes in an input sequence shown in red and then generates an equal-sized output sequence in green, right? So then there are three main components I want us to look at here, right? The first is the self-attention, right? It helps the model focus on like past tokens when predicting the next set of tokens, right? It uses query keys and like values matrices to determine how much attention to pay to different tokens. I mean, the self-attention here is really masked attention, right? In terms of like language modeling and decoding, meaning that you always focus on prior tokens when generating the next token, right? You don't look into the future, right? So for simplicity's sake, I'm just calling it self-attention. The next component is like layer normalization and residual connections. And this is needed to like sort of stabilize your training and like avoid exploding or vanishing gradient problems, right? And the final component is the feed-forward network, which is a simple linear layer, right? And it kind of just does the simple matrix multiplication of multiplying an input tensor with like a weight tensor and you get a result, right? And so the feed-forward network is matrix multiplication. Like the self-attention is also made up of many smaller matrix multiply matrix multiply operations. So let's focus more on the self-attention layer here, right, which is arguably the most important component of the decoder block. So this is kind of a busy diagram, right? I've tried to like make it as simple as I can, but what I'm showing here is one single decoder block, right? Again, you take an input there are, let's say, n tokens in your sequence, right? Each token has a dimensionality of dm, and then you generate an output for it. The first thing that you're seeing on the left here is a set of like linear projections, WQ, WK, WV, to generate your QKB matrices. This is you're generating a smaller dimensionality than dm that you started with, and so the first two matrices, the queries and the keys, are multiplied together, which sort of results in an n by n S or a score matrix. And then you apply the softmax operation on it to convert the scores into like a probability. And the probability is just in terms of like how much importance do we give to like all the other tokens for this current token. And finally, right, there is yeah, and then like the other thing here on this diagram is the fact that you have n heads. So you kind of repeat this process n heads number of times, and then that's kind of why this becomes like multi-headed self-attention. Right. So the result of each attention head is concatenated together at the bottom there, and then we apply another lot of linear projection, right, which results in the same size like output. So this kind of critical block diagram, right, that is in every single decoder layer of a network, and a simple like network today, like a Llama 3.1 8 billion model, which contains like, let's say 32 decoder layers, you see sort of this operation repeating 32 times, right? So and you see this operation contains a set of like sub-operations, which are all matrix multiplication. So in order for you to get the performance you want, if you want to optimize your performance, you want to optimize each of these sub-operations and this operation, right? So is self-attention optimal, right? Not always, right? Especially when we have like a longer sequence length. And it's not as efficient as it's a generic matrix multiply kernel that we use in our feed-forward blocks. And why is that, right? To find an answer to that question, right, let's wear our hardware hat and measure the flops and the bytes like we saw on the previous slide. So for like one head, right, and a sequence of length n, where the sequence length n is like input plus output, the attention score matrix is generated by multiplying the Q tensor of size n by dh with the transposed K matrix of size dh by n. So, and then if you remember the 2 times m dot n dot k that I showed you earlier, right? If you multiply that, you basically see that the number of estimated number of flops here are 2 times dh dot n to the power of 2. So, and then I guess when you have like for the entire model, you have a batch size of b, you have a bunch of layers, you multiply all of that together, it becomes this huge number. So what I want you to focus on is the quadratic scaling complexity with the sequence length n, right? Let's look at bytes next, right? The size of the score and the probability matrix are also n by n. So when you generate them and when you store them, right, you again need to be reading and writing from memory. The size of these matrices are again have a quadratic scaling with sequence length, right? So that's kind of the observation, right? That you have a quadratic complexity with the sequence length, and we know that a longer sequence length is desired, right? Why is that? That's because a longer sequence length helps you build a bigger context. It helps with performance. It also helps with when you go into like multimodal models, like on images and videos. There are many more tokens there, right? So you want to scale your models for a longer sequence length. So how do you do that? So the solution, right, that we came up with, that folks came up with, was flash attention, right? And this is a result of like really smart hardware software co-design. So the authors of this technique, right, approach implementing the attention algorithm in an input-output aware way, which is accounting for the amounts of reads and writes that are triggered in the hardware. So to understand this technique, right, let's understand the hardware first. So I've tried to create this simple like machine model for like a modern GPU, right? So you can think about a GPU as a sea of cores, right? And each core is capable of executing a program in parallel. Each of these cores contain like a small SRAM or a small piece of memory. Since it's quite close inside of the core itself, it is really high bandwidth, right? It's really fast, but it's pretty small in size because of like area considerations for the silicon. And then you also have like an external memory on the right that I've shown as the HBM, which is larger in capacity. Since it's further away, it has a lower bandwidth connectivity to it, right? So like notice, right, the difference, there's an order of magnitude difference between the bandwidths when you are talking to the SRAM in your core versus when you have to go out to the HBM. Right? And that is the critical observation, right, that was exploited in order to build on and develop flash attention. There is also like another piece of memory here, like an L2 cache, right, which I'm not showing, mainly because that's not programmer visible. Right? So for this discussion, let's just focus on like the SRAM and HBM. So flash attention was the new sort of attention algorithm, right, that computes attention with like far fewer memory accesses, and it was developed in 2022. Right? It does two key things. Right? First, it computes the softmax without requiring the entire attention score matrix. Right? And second, it removes the need to store the score or the importance matrix, and it can just recompute them when you're in backward pass. So this is a diagram that I've drawn to sort of describe how flash attention works at a high level. Right? Remember the same Q and the K and the V matrices that we saw earlier. These are stored in HBM, right? If you remember from the previous slide, the way you would do it, you have to multiply Q and K. So you would read these big matrices from memory. You would do that big operation. You will generate S. You would write it back. Then when you have to compute the softmax, you would read it back again, do it, and then write it back all out. So instead of doing that, what the technique applied here is that you kind of use the strategy of tiling. So what tiling essentially means here is you load a smaller block of inputs from HBM, right, into the SRAM that you saw inside of the core, right, and then you compute attention with respect to only that block, right. So here the key is partitioned into like just two blocks here, right. So is V, and the score and the importance matrices are computed on these two blocks in parallel. Right? So to sort of accompany this tiling strategy, what you also need is another innovation, which is how you're computing the softmax, which is the algorithm is called online softmax. And what it does is it computes like the local softmax with respect to the block itself, and then it just does some rescaling to get the right output at the end. So at the bottom, you're seeing these L1s, L2 rescale factors that are computed, and then when you after you get your importance and probability matrices, and when you multiply them with V, you generate your output O. That's where you apply your rescaling to get the same results as if you had looked through the entire scores and P matrices to make the operation. So and then during like backward pass, so this is the forward pass that you make when you're going through in the training or in inference, and then in backward pass to update your weights, you can just recompute your S and P matrices if you remember the L scaling factors, right? So the decision that was made here algorithmically was it's cheaper to recompute than it is to store these matrices into memory and then bring them back in. So what is the result of these like optimizations, right? You see a massive 2 to 4x speed up improvement in the runtime and a 10x to 20x improvement in memory savings for like the longer sequence lengths that we care about. So even with all of these optimizations, right, what we saw was like the flash attention 1.0 is still not nearly as optimized as your generic matrix multiply. Right? It only reaches about like 25 to 40% of the maximum flops that your machine might be able to generate. Right? So what can you look to optimize next? And what you could do is you could look inside of what's happening in the cores, and you can try and improve that further. Right? And that is where Flash Attention 2.0 came in, which was developed in 2023. So kind of remember the sea of cores machine model I set up earlier. Right? So each core works on a program in parallel. Right? So what you want to do is you want to exploit this parallelism to get better performance. Right? So you want to make sure each of your cores are busy doing like real useful work. So what Flash Attention 1.0 used to do was it would do a single head on a core, right? And then you would have the number of heads that you have in your model and times the batch size amount of work to fill all of the other cores. Right? But like we said, right, we want to think about like longer sequence lengths because that's important for our use cases. When you have longer sequence lengths, right, you usually have like a smaller batch size or you have a smaller number of heads. So that's not enough parallelization to be able to use the GPU effect efficiently. So what can you do? So what you can do is you can additionally parallelize on the sequence length dimension. So let's kind of go back to our diagram that we saw earlier. And this time, what I'm showing is I'm also breaking each of my queue blocks into different rows. And if you look at the computation that a single row here does, right, it requires the entire K and the V matrices, but it doesn't care about any of the other queue components. Right? So you can very smartly execute an entire row on a core, and you can do the other rows on different cores. So you are able to break the sequence length n on the queue here into like rows of whatever size you pick. Right? You could, if you want to fill up C cores, you can do a split by into C chunks, and then you can execute these sequences in parallel because these are completely independent with respect to each other. So that is a really neat observation, right? Because you are now able to parallelize a lot of work, and you're able to make use of your GPUs in a much better manner. So that kind of sets up how do you best schedule work across the cores. Now, within a core, you still have many threads, right? So you also have to decide, okay, how do I best execute work across the threads inside of a single core? And here comes another optimization, right? Focus is paid to minimizing the reads and the writes that are needed to store the intermediate results in the coupled SRAM of the core, right? So even though the SRAM is still super fast compared to the HBM, right, it's still not free. You still have to compute something and store it back and then read it back again. So you can try and optimize your algorithm such that you try and reduce the amount of reads and writes to that individual coupled SRAM as well. And that's kind of what the authors did, right? They proposed a smarter way to partition the Q, K, and V across the threads to avoid needing different threads to synchronize and write intermediate results, and then you don't have to reduce those results at the end either. So that's great, right? You're able to like build on some more observations. You kind of made even more progress. You pushed the envelope even further, right? And that the story doesn't end there, right? Then folks realize that there is even more performance to be gained because as years pass on, right? The machine underneath changes. It has new capabilities. It is able to do work even faster and even better, right? So Flash Attention 3.0, right, was developed in 2024, right, which sort of takes a further stab at these hardware-aware like optimizations. It like exploits like new capabilities like asynchrony between computing work on the execution data path, which does the matrix multiply with like the DMA engine to like load and move data. So you can sort of overlap compute and data movement. What they also looked at was using doing a lot of computations in FP8, which is lower precision than like FP16 or BF16, and lower precision helps you get like Like FP8 has like twice the amount of math throughput compared to like FP16. Right, so I mean, I won't go into the lot of details of like what these optimizations were done, but like I'd encourage folks to like read the paper and like learn more. Right, what I'm trying to like build here, right, is we kind of looked at 3 iterations across 3 years of optimizations on flash attention, right, which is the technique being applied to improve self-attention, which is a very crucial part of our transformer-based models. And this attention, it sets up, defines how much performance you can get from your model, right? And this sort of iterative process of looking at the hardware and software and making improvements demonstrates like this very strong trend of optimizing performance, right, with hardware design and constraints in mind. So to kind of sum up, right, I want to leave you with these 3 key takeaways, right? First, we took our first steps towards wearing the hardware hat in understanding the building block of deep learning models, the matrix multiplication. We also established a very simple GPU machine model. Second, we saw that hardware-aware optimizations are the future to making these deep learning models even faster. And then we saw 1 and 2, right, with one such application to learn this paradigm, which is via flash attention. So I encourage you all to further the path of hardware-software co-design, right? And I can't wait to see what new optimizations you all uncover next. Okay, thank you. Yep, thanks for having me. I'd also like to thank the organizers for all of the hard work they've done in putting this like wonderful event together. Thanks. Yeah.
Thank you, Naman, for being here with us in Lisbon, and especially for the amazing keynote that you just delivered. And do we have any questions for Naman? Yeah.
So you say that we should be aware of hardware to optimize it, but shouldn't we also consider designing the hardware with further software and algorithmic optimizations made beforehand? Or
Yeah.
do we just build on the hardware that's already done?
Right. That's a great question, right? I think that's exactly where industry is headed right now, is because so you understand that the next level optimizations come when you look at hardware software co-design, right? So one way to approach this is something like what we saw here, that okay, you have the hardware constraints and capabilities, and then you try and tweak software to work best on it, right? And then the other side to the story is, right, having an understanding of the kind of evolution of the software, right, how models are evolving, what are the operations you need to be doing, that feeds back into designing the hardware to make those operations better. So for example, right, in Flash Attention 3.0, right, I showed you that you kind of notice that you want to do a set of like matrix multiply operations. To be able to do the compute, you need to bring in the data which is stored somewhere further away, right? And the observation is that you can bring in data, right, that you want to work on next while you're computing the previous results, right? You can do this sort of like pipelining, and this is exactly what the asynchrony between compute and data movement was, right? So that this observation fed back into the hardware design, and then in hardware, folks build things like asynchronous compute and DMA to be able to overlap these things better, right? So that is exactly how I think the future looks like, which is you feed in the work that you need to be doing into the hardware development, and then you improve the silicon even better to make it all work, the ecosystem work better. Yeah.
Okay, any other questions?
Hi, Naman. Thank you for the great talk. I would love to know, there are a lot of advances in flash attention and a lot of iterations to solve the memory optimization problem. I would love to know, what do you think about Mamba, and does that make flash attention redundant? And what will happen to the future GPU architectures because of Mamba?
Right. Another good question, right? So Mamba is another interesting, like, different paradigm of models, right? State space based models. They have, in fact, I would say that a lot of state space based models and how Mamba architecture is developed, that is developed with keeping hardware constraints in mind, right? You're trying to like reduce the need for this quadratic complexity on that you have in attention is the problem that Mamba is trying to solve, right? So you want longer sequence lengths, right? You want a sequence length of, I don't know, 128K, maybe even a million, right? To be able to like look at a huge sort of book and then make some decisions. So if you use standard attention and you see that quadratic complexity, right? That's a big problem. Flash attention is trying to solve that. Mamba is another kind of way of avoiding the sort of squared complexity on sequence lengths. So I would look at them as sort of solutions to the same problem, and we still would need, I think, something like this, because Mamba is yet to prove itself in all various like use cases and various models that we want to see. So we do want to keep investing in improving flash attention, because attention and transformer based models work great. Mamba is up and coming, it works really well as well, and the GPU development, the hardware needs to be generic enough to be able to like to serve both these kind of models, and then also the third kind of model that some of you guys will develop like 2 years from now, right? And that still needs to work really well on the given hardware. So yeah, I think that's kind of how I see it evolving.
Okay, any final questions for Naman? Okay, that concludes the session. We are going to pick the winner for this session, and also Naman would be in the second stage to answer any other questions that you may have. So the winner for this session is Tomasz Gloria. Could you please come on stage, please?
Yeah, thank you. Yeah. Okay. Ready? Yeah.
I just wanted to thank everyone for coming. This was the last keynote of SINFO 32. This was our most ambitious edition yet. We've had great numbers, and we're very thankful for everyone that came. Thank you so much, and see you again next year.